Hello. In this video, we're going to look at divisibility rules and how we can use those to express numbers as products of their prime factors. Any natural number can be written as a unique product of prime factors, and we can use that prime factorization to do any number of things. So that's what we're going to talk about today. Just to be clear, a prime number has exactly two factors, one and the number itself. So examples of numbers that would be prime would be things like 7, because 7 is only divisible by 7 in itself. 41 is an example of a prime number. There's any number of those. Composite numbers have at least 3 distinct factors. So a composite number could be, for example, 9, because it's divisible by 1, 3, and 9. You could have numbers that have a great many number of factors. So something like 24 is actually a relatively small number with a lot of factors. 2, 3, 4, 6, 8, etc. The number 1 is neither prime nor composite because it doesn't fit either of these definitions. It's not prime because it doesn't have 2 factors. It just has 1 factor, just itself. And it can't be composite because it doesn't have 3 or more factors. So 1 doesn't really count as either prime or composite. And that actually ends up being really handy because most of the time we're dealing with is a number a prime factor of another number. So a prime number we're looking to see, is it a prime factor? 1 is a factor of absolutely everything. And because it's a factor of everything, it's not actually useful in telling us anything about the distinct properties of that number. 1 is very useful in a lot of other ways, but not for factorization purposes. So here are some divisibility rules. Probably most of them are familiar with you. For you, divisibility by 2, we've got even numbers ending in 0, 2, 4, 6, or 8. The reason that works is because let's say I have a number like 96. That number is equal to 90 plus 6. The tens place, the hundreds place, those are always going to be divisible by 2 because 10, 100, 1,000, those are all divisible by 2. So if the units digit is divisible by 2, then by the distributive property, this whole number is going to be divisible by 2. For divisibility by 3, the sum of the digits is going to be divisible by 3. So let's say, for example, we have the number 417. If I add these digits all up, 4 plus 1 plus 7, so I don't need an equal sign here. 4 plus 1 plus 7 equals 12, which is divisible by 3, and therefore this whole thing is divisible by 3. For divisibility by 4, we need the last 2 digits to be divisible by 4. So a number, for example, like 7,924 would be divisible by 4 because 24 is divisible by 4. The rationale for this is very similar to the rationale for divisibility by 2. This is 7,900 plus 24. And if I have something 100, that's always going to be divisible by 4. So if the next 2 digits are divisible by 4, then so is the whole number. Just the explanation for the divisibility by 3 takes a little bit more of a lengthy proof. So I'm not going to do it in this video, but certainly that proof is readily available elsewhere. Divisibility by 5, the number ends in 0 or 5. Again, a very similar explanation to the divisibility rules for 2 and 4. So if I have a number like 745, this is 740 plus 5. So since that tens place is always going to be divisible by 5, if the ones digit is divisible by 5, then so is the whole number. Divisibility by 6 has to have divisibility by 2 and 3, and that is because 6 is simply 2 times 3. So to divide by 6, you could divide by 2 first and then divide by 3. So as long as your original number is divisible by both. So for example, a number like 5, 9, that's 4. Let's say 594, because the last digit is 4, it's even. 5 plus 9 plus 4 is 18, which is divisible by 3, so this number is divisible by 6. Divisibility by 7, there are rules. Remembering those rules and applying those rules is usually harder than just actually dividing by 7. Dividing by single-digit numbers isn't particularly complicated. So if I was trying to determine if a number like, for example, 7924 was divisible by 7, I would simply actually just do that division. And in this case, I find that it is in fact divisible by 7. Divisibility by 8, this one starts to get a little less useful because it does mean we're looking at a 3-digit number, and it's sometimes a little bit tricky to determine if a 3-digit number is in fact divisible by 8. But let's say, for example, we had the number, I don't know, 5,184. Let's say 75,184, or it was an even longer number. I need to look at these last 3 digits. Now, I don't immediately know if it's divisible by 8, so I have to check, but it's a little quicker to check if a 3-digit number is divisible by 8 than to check if that entire 5-digit number is divisible by 8. So I can just look at 184 divided by 8, and I get 23. So yes, that is in fact divisible by 8. And again, the explanation, very similar to 2 and 4. This is 75,000. Any thousands place is always going to be divisible by 8 because 1,000 is divisible by 8. Divisibility by 9 is a similar rule to divisibility by 3. So if the sum of the digits is divisible by 9, so let's say we had, for example, 594, which was divisible by 3 because 18 is divisible by 3, is also divisible by 9 because 18 is divisible by 9. The proof of divisibility by 3 and divisibility by 9, those two proofs are very, very similar. I'm not going to do them here because they do require a little bit more formality. Divisibility by 10, I'm sure you're all aware, the number ends in 0. And divisibility by 11, it seems like a more complicated rule than it is. You're alternately subtracting and adding digits starting on the left and see if the result is divisible by 9, or by 11, sorry. In practice, this is actually not that complicated. So let's say, for example, I have the number 79385 as a hypothetical. And I want to know, is that divisible by 11 or not? Now, in most cases, if you're just looking at a 2-digit number, you're going to know, for example, that 66 is divisible by 11. If I apply this rule here, alternately subtract, start with subtraction, and then add. So 6 minus 6 is 0. 0 is divisible by 11. 0 is divisible by everything. So 66 is divisible by 11. But you're usually not going to have to apply this rule to that number because obviously repeated 2-digit numbers, or a 2-digit number that is just the same digit repeated, is divisible by 11. But in this case, I go 7 minus 9 plus 3 minus 8 plus 5. So 7 minus 9 is negative 2 plus 3 is 1. 1 minus 8 is negative 7. Negative 7 plus 5 is negative 2. This is not divisible by 11. So this number is not divisible by 11. Usually the results you'll get, because you're just going to be adding and subtracting digits, they'll waver back and forth across 0. If it is divisible by 11, you'll see a lot of, I get all the digits, subtract, add, I end up with 0, then that number is divisible by 11. You can also end up with 11, you can end up with negative 11. For very long numbers, you can end up with 22, negative 22. If it's divisible by 11, the result is divisible by 11. So we use those rules to express numbers as products of primes. So 385, for example, I can see right off the bat 385 is divisible by 5. It is also divisible, I believe, by, well, we'll see. But the first one I see, I divide that out. So 385 divided by 5 is going to be 77. Yes, it is divisible by 11. That's what I was thinking, because 3 minus 8 is negative 5. Negative 5 plus 5 is 0. But I divide out the first one I see. Once I get to 77, I can see much more clearly that that is 7 times 11. 5, 7, and 11 are all prime numbers, so I have finished. The product of primes, I need to actually express it as a product of primes. This tree is how I divided it out. That's not my answer. 385 can then be written as 5 times 7 times 11. And knowing these prime factors can help me do a number of operations and I guess, analyses of 385 to sort of see how it's going to behave in different situations. If I want to determine if a larger number is prime or composite, so it's prime if it doesn't have any factors other than 1 in itself. But I don't have to check every single number between 1 and 179 to decide if they're factors, because every number that has non-prime factors can still be broken down into prime factors. So for example, 24 can be written as 4 times 6. 4 and 6 are not prime, but I can break it down further. 4 is 2 times 2 and 6 is 2 times 3, so 2 times 2 times 2 times 3 would be 24. So if a number can be factored, it has prime factors. So 179, I really only have to check prime numbers, and I only have to check prime numbers up to the square root of the number. Because if a number is divisible, well, basically every factor comes in pairs, right? 10 is divisible by 2, but it's also divisible by 5 because it's divisible by 2 times 5. The square root of 10 would be slightly more than 3. One of those factors, 2, is less than the square root, and the other factor, 5, is greater than the square root. So for every factor less than the square root, there's a corresponding factor greater than the square root. Now, I don't know exactly what the square root of 179 is, but I don't need to know exactly what the square root of 179 is. I just need an approximate because I just need to test whole numbers. So I know that 14 squared is 196, so it's got to be less than 14. So the only prime numbers I need to check 2, 3, 5, 7, 11, and 13. These are the only prime numbers that are less than the square root of 179. So I can tell right off the bat that it's not divisible by 2 or 5. I don't even really have to think about those ones too much. I have to do a quick check on 3. 1 plus 7 plus 9 is 17, which is not divisible by 3. I'm going to check for 11. 1 minus 7 is negative 6, plus 9 is 3. That is not divisible by 11. And for 7 and 13, I'm actually just going to try the division. So 179 divided by 7, 17 divided by 7 would be 2 times with a remainder of 3 because 2 times 7 is 14. 39 does not divide evenly by 7. It would be 5 with a remainder of 4. So it's not divisible by 7 because there's a remainder. And 179 is likewise not going to be divisible by 13. 17 divides into 13 one time with a remainder of 4. 49 is not divisible by 13. It would be 3 with a remainder of 10. So not divisible by 13. So this number is prime. If I found a single factor, it wouldn't matter if there were more factors. As soon as I find a factor other than 1 or 179, I can conclude that the number is composite. But if I'm going to conclude that it's prime, I have to test it with every prime factor less than its square root.